Okay, so NoSQL Postgres roadmap. What is it? The most slides from the talks are made by Oleg Bartunov, who is Postgres major contributor and who is principal author of many NoSQL features in Postgres. Unfortunately, he couldn't come here. Oleg is working on Postgres since 1995. He has really great experience, and he is one of the oldest members of Postgres community. And here you can see all the things he contributed in the elephant shape. So JSONB is one of the most important, probably, contributions. Okay, so NoSQL story of Postgres started when we, with Oleg, worked in Rambler. It was #1 internet portal in Russia in beginning of the century. And it was built on Postgres. And there was a news service. And there was some typical join between two tables. And this join was slow. It was 6th version of Postgres at that time. But already Postgres contained arrays. And there were some ideas how to make indexing of arrays. And the thing which was done at Rambler by Theodor Sigayev, one more, my colleague, which is also a major contributor of Postgres, he invented a good way of indexing of arrays, a good way of array index search, which was based. If you can't hear me well, then I move to this mic. So the idea was changing the join with intermediate table to join with array. So it was done using gist indexes created by Theodor Sigayev, and it got a performance gain 30 times. It was really a great result. We were also impressed by that and understood that extending classical database features is probably one of the important Postgres advantages. The next task we had to solve is storing polymorphic data in the database. So the problem was such as we needed to make a catalog of different things with different properties, and how to solve it. You know, there is EAV, very slow, classical EAV approach, or maybe you get a table for each class of the objects. It is also sometimes maybe inconvenient. And so we decided to create a new data type for Postgres. It was called HStore. H means that it was inspired by Perl hash. And it contains a set of keys and values. This thing was also supported by gist index search. And that's why it became rather popular. You see, here is a graph of popularity using Google Trends. HStore here is red, and it was popular very old, at very old times, and only in 2013, JSON overcame it in popularity. Later, I will explain why. So, when JSON was decided to be used in Postgres, it had a lot of drawbacks in comparison with HStore. HStore was fast because it had an optimized binary storage structure. JSON was text. And to process it, to search it, you needed just to parse it each time. It is very, very bad, very ineffective. But HStore is one-level hash. It has no nested structure. JSON is nested, and in the form of JSONB, which was invented later, it also has an optimized storage structure, so it is also fast. The story with JSON started in 9th versions of Postgres. There were several attempts of implementing JSON. First attempts were just text storage of JSON, with some verifications of its syntax and so on. But practically useful form of JSON was, of course, JSONB, which was contributed in 2014. Why? Because it allowed to make a fast access to the data stored in JSON. JSONB has additional, it is pre-parsed. So to search for a key in JSONB, you don't need to parse all JSON. And the intersection on the popularity graph is just a pairing of JSONB. So without JSONB, JSON was not very good. It was slower than HStore. But it overcame HStore in popularity only when JSONB was done. And the next step, which we expect, is support of SQL JSON standard. It's a new standard. And now a work is done. Here is a mistake. It was expected in Postgres 10, but now it is expected in Postgres 11. So the patch is very big, and we were too late to submit it to Postgres 10. So now we have two JSON data types in Postgres, JSON and JSONB. Let's compare. So JSON is a plain text storage. It means that you have a preserved order of keys. It can contain white spaces, so some formatting, and it can have, of course, duplicate keys if you need that. JSONB is fast, maybe 1,000 times faster. But the keys are unique, and of course there is no conservation of the order of keys. So the keys are sorted by some technical reason by length and key. But JSONB is supported by index search, by GIN index search. JSON is faster in the search, of course, because you don't need to pre-parse it. If you, for example, make a write-only database, then you don't need JSONB. Yeah, you only insert JSON, and you are happy. JSONB occupies greater disk space than JSON because it needs additional space for the information of the structure of the internal index, which helps to find the keys. It occupies time, and if the keys are long, it may be seriously greater in size than JSON, maybe 2 times. So JSON is not completely useless. In some cases, you use JSON. In some cases, you use JSONB. But the general recommendation is use JSON only if you understand what for do you use it. By default, use JSONB.
Excuse me?
Yeah.
Nowadays, when people say they're using JSON, do they often mean JSONB?
Yes.
Okay, thank you.
Okay, and of course, very often when you design your database, you need to make a decision what to store in JSONB, what to store in regular fields. So there are some maniac people who store everything in JSON. Usually it is not effective. First of all, the problem of JSON is that you need to store the keys, not only values. Storing keys is ineffective because they are repeated many times. But in some extent, it is solved by compression. Here you see 2 links to some compression solutions for JSON, which are available on GitHub and compatible with any version of Postgres, any modern version of Postgres. Compression? Sorry? It means, no, it means some special compression for JSON, other data type, which has some table-level dictionary of the keys. And the idea is that you do not store the key, you store only a number of the key. And the keys are stored in some dictionary. This is the main idea. JSON is not very strict, so you don't have constraints. You don't have data types. It's worse than regular database columns. So always you need to decide where to use JSON, where to use classical database. Okay, so how to work with JSON and JSONB? Yeah?
May I ask about the SQL JSON, the upcoming...
I will come to this later, the SQL JSON. So first I describe the classic JSON, JSONB, and then come to SQL JSON. Okay, so how to create JSON and JSONB? First, you can convert it from textual representation, or may use constructor functions, so you may convert database structure to JSON structure. How to retrieve information from JSON, JSONB? There are operators right arrow and right arrow arrow. Difference is that first of them extracts JSON and the second extracts text. There are two different operators because each operator in Postgres needs to have some definite data type it returns. Okay, so here are examples. You may later study it in detail. Also, there are some functions that are converting JSON structures into rows. JSON each text, JSON array elements. These are four functions which convert JSON structure to rows. Why four? Two, because they may return text or return JSON, and two more because they process arrays and objects. So four different functions to convert JSON to rows. Okay, how to search data in JSON, JSONB? First, most simple search is done when you are looking for a definite value of some definite key. It is easy, and of course, it can be supported by regular functional index. But for that, you of course need to know the key. And each key is indexed separately, if you like. Okay, other operations. You can, by operation on the number 2, returns, so the right operand is the path. You can pass the path as an array of keys. And the operation number 2 extracts the data by array path. And also there is a SQL way to search in JSON. On the previous slide, I showed that there are functions that convert JSON structure to rows. By that, you may search by regular SQL expressions. For example, you see in number 3, you change the JSON into some rows and search. Of course, it is slow and not supported by any index. Okay, another search. There is a contains operation at greater. Which does it mean? It does mean that some JSON contains some JSON as a subset, contains it inside. For example, suppose that the data stored in JSON field is like that. You have a company name, and it has an array of offices. Offices can be main or secondary. It can be located in some city. It has area in square meters. So, if you want to search a company with office in Jerusalem, then you use the contains operator with the following JSON at the right. So, office in city of Jerusalem. The JSON above, it contains this. So, the result is true. More complicated search can be done, of course, by SQL. For example, which company has an office in any of the cities? So you just combine this with SQL OR. Or you can do it in SQL way. So just convert this to rows, to row structure, and then apply simple where. What can be said about these two variants? So first of them needs 2 index searches. If you have index support for this operation, there's 2 index searches. And the second variant, unfortunately, has no index help. Okay, you can make some more complicated example. For example, which of the company has its main office in any of these two cities? Following the previous example, you may think that just adding "and" with main office solves the task. But unfortunately, it is not true. Other variant, which is below, is better. Why? Because first, in fact, it means that you are looking for a company who has a main office somewhere and an office in any of these two cities. So just, it is a very popular mistake in these queries. So the second variant is correct. The "and" condition goes inside the JSON match, and they are joined by "or." Okay. Of course, it can be written in pure SQL, like that. But SQL allows more. For example, let's add another search criterion. We need big offices, greater than 500 square meters. In SQL variant, you just add the greater condition here and have no problems. But there is no way to use JSON match here for this kind of conditions. Strange, but it is because SQL is really a flexible language. You may do anything on the SQL level, but you can't do it inside some JSON match. And it's a problem, yeah?
But when you use SQL, it won't use indexes?
Of course, no indexes here. Because you see, you use the SQL query on the array, on the JSON array elements. So you extract array from JSON.
Could I give the functional index?
But which function? This is hard to build a function. So in general case, there is no way to build such function. Of course, in some cases, maybe you can invent a functional index for that, but not for the general case. Okay, so other things which can be done with JSON. There are operators to check if a key exists on the top level, if any of list of the keys exists on the top level, and all of the specified keys exist on the top level. Okay, so after that, what do we understand on JSON? So a simple search by a fixed key is good, is fast, if you use simple B3 functional index. Okay, but its usage is very small. The next way to search in JSON is use the contains operator. It is much more functional. It can be supported by gin indexes, but there are problems because it is not very flexible, and it is not very effective on complex queries, because I showed you an example where you needed to perform two different queries on index. It's not good because you have to make two index searches, maybe instead of one. One index search may be faster. Okay, so something is really needed to be done. Okay, about classical JSON, there is a very good talk by Christoph Petus, so this is a link to it. Welcome to read it. Okay, so this is a painting which we met in the hotel in Warsaw at pgConf Europe, and Oleg decided to use the characters from this picture to make a dialogue with you during this presentation. So this family is searching for a good JSON solution, probably. And they find that JSONB is great, but not very. Okay, so it has no good query language, probably. Yes, so just a contains operator is not enough. For example, you need to find something red. How to do this? Okay, it's no problem. If you can contain the red color in very different places of your JSON. But for example, you come to a shop and just need to buy something red to ride your red car, for example. So if you try to do this in classical way, it is a very complex SQL query. It's written here just for fun. Nobody uses it, of course, but it works. Okay, of course, it is good. It is simplified with contains operator, but not very. It also works. So to improve this, Oleg and Theodore invented JSQuery, which was then implemented by Alexander Korotkov. JSQuery is a special data type which provides a query language for JSON, JSONB, better. So JSQuery is an extension that allows you to write the query like that. So the main idea is that you can write paths as wildcards. It is also available on GitHub, and you can download it and build with any modern version of Postgres. It's very convenient, and it provides more operators. So the main idea of JSQuery is defining a query as a new data type. And there is a match operator. You see value, which is JSONB, matches some condition. And this condition is the JSQuery data type. Okay, so come back to our examples with offices. So main office in Jerusalem and Tel Aviv with area greater than 500 square meters. You can write it in JSON, in JSQuery. And this is the query from here to here. So it contains great operator, it contains and so on. Okay, and you may create indexes to speed up the execution. So there is a lot of operator classes for JSONB, and you can make indexes in different way. So now 4 exists, but you can extend this. So if you want to search keys and values indexed separately, then use JSONB ops and so on. So from this table you can understand which kind of index is better for your query. And of course, JSONB not always is more effective than a simple functional B-tree index. It also still works. The future, next step of extending the JSON indexing is the idea of smart indexes. Just see some presentation of that. Okay, so what else can JSQuery do? So path is some dot-separated construction with possible wildcards. There are three main elements of the wildcards. So this symbol means any array element number. So it means that A, B, and some array element is equal to 2. The percent sign means any object key. Okay. And the star asterisk, it means either key, either index of array, anything. And dollar means current element. It may be necessary, for example, in cases like that. So by this expression, you obtain some element, and then you need to compare it with something. Also, complex keys are quoted. Okay, so this is the general way of writing JSQuery expressions. Also, you have operators for each key. For example, if you search company with office, any office in Jerusalem, you use this sign. But if you search for companies which have all offices in Jerusalem, you just add a colon. Also, there is an operator for extracting size. JSONB is you see, rather rich in functions. It has more things. Also, it has in operator. It can perform array intersection and search for array inclusion in forward and reverse way. The forward way means that you use arrays that contain specified values. And the reverse inclusion means that your array contains the values only from the specified set. So this is which you can perform with jQuery, and this is supported by indexing. Also, jQuery has functions to check type of elements. You can check if the element is array, is a number, an object, a text string, or is Boolean. Also, there is some optimizer inside jQuery engine, and you can pass hints to it. For example, you can ask it not to use index for some part of the query. You do it in the case when you understand that this part of the search is not effective in index and better to compute it on the recheck phase of the query. Also, jQuery can be used to constrain JSON schema. For example, this is an example how you restrict the office's structure. Area should be a number, and it should contain a city. So jQuery can make your JSON more strict. Also, JSON has some aggregates. Array aggregate, which just joins JSON values into array, JSON aggregate, which aggregates values into JSON array, and JSON object aggregate, which aggregates it into JSON object. They are useful, for example, if you want to return some complex structure or perform several queries in one time. Okay, there is a classical example when you have a database with orders and items of these orders. And for example, let you want to select orders together with its items in one query. Then you select orders and select items in JSON field by subselect. So it's a kind of post-relational query, so you get some nested structure just from one SQL query. So if you need to order the items of the order, then you need to use some subselect because ordering is performed after aggregation. Of course, you may define user aggregates on the JSON, and here I need to notice that PLv8 is the most effective procedural language for JSON. Why? Because at present time it's the only language which has built-in JSON support, so you don't need to parse JSON. It just comes inside the v8 engine as JavaScript structure. For example, this function aggregates the items and also calculates the total price of your order, for example. So creating such or more complicated aggregates is possible, and it solves some business tasks. Okay, some Russian. Maybe we can, okay, skip it. Also, you can join several queries in one. For example, you just need to extract much information, and you have no access, for example, to begin a transaction, but you need to perform a transaction. You can do it with JSON. Okay, now something about trees. This is a big problem, and I will not tell this in detail here, but if you want, then you may look it in the slides later. So, for example, let you have a tree table with a link to the parent node. And the problem is to construct a JSON structure containing a tree with nested nodes. How to convert a linear table to JSON tree? Okay, it can be done in many ways. One of them is here. Of course, CTE is the thing that is usually used to process trees for recursion in PL/SQL. So this is an example of CTE, which extracts tree with paths. But you can't collect a JSON structure, a single JSON structure with CTE, because there is such a feature, or anti-feature of Postgres CTE, is that you can't use aggregates in its recursive query part. That's why you need to aggregate over the result of CTE query. So you just need to write a custom aggregate function and process the tree by this function. It can be done. Here is an example in PL/SQL, but in JSON, in PLv8, it should be, of course, more effective. Okay, so study it later if you want. One more important detail in using JSON. Please know that array indexes in JSON always start with 0, not with 1 as in SQL. Okay, so now we stop the JSON-B topic, but only some note. It is very good idea to write queries like that to set. This is called subscripting. So you can do this with arrays, but you can't do this with JSON. It's a problem, but there is some solution. Probably it will be committed soon to Postgres. And please note that JSON-B may be very, very big, very ineffective if you use long keys. So you can really use long keys, up to 1/4 gigabyte. Don't do like that. Okay, so now our family comes back, and the idea is that they discovered that modern JSON standard supports modern SQL standard, the standard of 2016, supports JSON. It is very unusual. They are, of course, surprised by that, but it is so. And next way is to implement, of course, this SQL standard. So this is a part of SQL standard 2016, which really contains some words, some pages about JSON support. So it specifies how JSON should be written in SQL, which operations can be done with it. But it's very, very big problem, because this standard is too late for Postgres. We made so big effort to support JSON, jQuery, and now we need to change everything, almost everything. But it's not impossible, and this work is done. First patch appeared previous year, more than a year ago, and we wanted to pass it to Postgres 10, but the patch was really too big, and it was difficult. It was difficult to commit it to Postgres 10. Really, working with big patches it just requires more man hours. It's not principal problem, but you need to have this man hours. And now we expect that Postgres 11 will have this patch. Okay, so JSON model here is similar to XML model in older JSON standards. And the problem is the standard has no data types, no data type for JSON. So it doesn't extend data types. So it is not very good for Postgres, because Postgres is effective and flexible with data types. Data types is that give you flexibility in indexing and so on. So, of course, our implementation is compliant with the standard, but it uses native data types, JSON and JSON-B. And when you look through the syntax of JSON path, you see that it resembles jQuery. Which does it mean? Probably we guessed we didn't take part in the development of the standard. Maybe guys from Oracle just read our JS query and improved it, or maybe not improved. Okay, so it also has dot notation, and it has some wildcards, some filtering expressions like that. But it's not equal to JS query. It's more complex. It has much more symbols to formulate. But in general, it is very, very similar to JS query and works in the same way. Okay. In Postgres, we need to make a special data type for JSON path. In the same way, we did it for JS query. Why? Of course, in the SQL standard, it has only textual representation, and just because there is no extensibility of data types in regular SQL. So, to make effective use of indexes, we need to make a separate data type for the query. Why? Because this is Postgres way how it finds which index to use. So a combination of data types leads to selection of indexes, and that's why we need to define a special data type for JSON query, for JSON path, and define an operator of the match between JSON or JSONB and this path. So just same as was done for JS query. Okay, so this is the example data set which will be used later. So it is some building with floors and apartments on the floors. Okay, this is a tree representation of the structure, a house with 2 floors and some apartments on it. Now we will see if we just use JS path $, we get the top of the JSON. If we use $.floor, we get the floors array, and so on. If we use like that, write like that, then we get the elements of the floors array, and so on. You see some array inside the index brackets and some range inside the index brackets. So this is an example of how to write this query. You see there are some new constructions with wrapper. What is it? Okay, it's a complicated thing. Maybe we will touch it today. Okay, and the filtering expression. We apply filter of the apartments with some specified area. Okay, this is the query. Here you see that there is a feature of passing. What does it mean? You can pass some values from SQL inside the JSON path. Here, $min is a variable that comes from SQL part. For example, now we pass the constant, but we also can pass an expression from SQL inside JSON path. We had no such thing in JS query, but JSON SQL allows to do this. Okay. And finally, we extract some field from apartment which has area from 40 to 90 and so on. So this is the general example how to use JSON path. You see, it is similar to JS query and rather simple. Okay, some other things that can be done. For example, floors that contains 2 apartments and so on. Also, it has wildcard search in keys. So, a lot of examples. I think we'll skip some of them. So, the query about red. So, you see that in JS query it is written like that, but in SQL JSON it is more complicated, unfortunately. So, really, SQL JSON is more verbose. But it's also maybe effective. So JSON path is cool, and To work with Postgres, it needs some extensions. Okay, extension means defining the operator, the thing which needs to use indexes. So we have defined an operator between a match operator between JSON and JSON path. This allows to perform JSON path search with index support. So there are several examples. I think also can skip them. JSON path operators. Unfortunately, JSON path is more complicated, and probably it will need some additional operator classes for indexes. But for most queries, the existing JSONB ops and JSONB path ops also are useful and really work good. So you see some example of plan of a query which uses index search, and it is fast. Okay, this is a comparison between a non-indexed variant of the query and indexed variant of the query. So this is a classic JSON, SQL JSON with JSON exists, and this is the same with the operator. And it really replaces sequence scan with index scan. It is much, much faster. Okay, so we decide that we can work with JSON path, and in future it will replace JS query. Okay, so what is done in Postgres? JSON path is not the only feature of the SQL standard. Of course, there are also constructors for JSON objects in the standard, and there are aggregates, which are similar to existing JSON aggregates. Okay, that's good. So this is the form of JSON constructor. You see it's much more complicated than in regular Postgres JSON. So it has a returning clause. It can return JSON or JSONB. It has also format, which means almost nothing for Postgres. And it has some additional things for nulls processing. For example, nulls may be converted into empty, into null values, or just remove keys with nulls. Also, there is, you see, some construction to provide non-unique keys. It's, of course, not compatible with JSONB, but compatible with JSON. Okay, this is implemented as some wrapper around the existing JSONB build object function. So it was not difficult to do. Of course, to omit the nulls, you see this construction, which helps to omit null, how it works. It's also done as a wrapper around JSON, about this function JSONB build objects. Okay, aggregates also with approximately same constructions, and object aggregate also, it's bigger array constructor, also with much features. So the main author of the standard was probably Oracle, and that's why it is very verbose. Okay, the functions to retrieve data from SQL JSON. JSON value extracts one value given a path. JSON query extracts some almost the same, but it extracts text. JSON table converts JSON structure to rows. And some functions to check JSON type, and if something exists inside it. All of this is implemented in our patch to Postgres, and all of this is expected to be merged in 11th version. So you see that there are a lot of strange and unusual things. Error handling inside JSON is very complicated, and some functions to process empty values. Also very strange, but it exists in standard. Okay, so this slide illustrates how the additional options to JSON query can change the result. It defines some wrapper, conditional wrapper, unconditional array wrapper, and some additional things. Why is it done? For example, it can wrap the result into an array, like that. Unconditional means wrap, not null value, and so on. So now we have no idea what can be used for, but it exists in standard. Okay, also JSON exists can be used to provide some constraints on the JSON structure. It is similar to things which can be done with jQuery, but with some more functions. You see, passing, for example, it makes it much more flexible. JSON table is similar to 4 functions that convert JSON to rows. For example, in this house, you can extract JSON table of all the apartments here with some big and complicated construction. And after that, you can perform SQL querying, of course, without any index support. Okay, so this patch is available on GitHub. We have some web interface to play with this. You can just try to learn SQL JSON with this example. Also, there are some standard is not available for free. You need to pay $400 to read it, but there is a technical report which is free. You can read it. Okay, so now we have already written the documentation for Postgres, but we need more examples. We need more tutorials. So we just want to encourage you to share your experience, try and write about that. Okay, so let's keep this. Okay, so this is a part of a table. This is a link to the full table. This table illustrates how many of the SQL JSON features are supported in Postgres, as we expect, and in other existing databases. So in Postgres, everything, all the features are supported except one. So the table is rather long, but it's all okay with Postgres. Other databases support standard only partially, including Oracle. MySQL and Microsoft SQL has some very, very limited support of this, but probably they will improve this soon. Okay, several words about compression. So compression. What can be ideas for compression? Main idea is to create a dictionary of keys and compress keys with replacing it with their IDs. Also, some delta compression can be used for arrays if they store similar data. Of course, we can use some standard compression algorithms as gzip and so on, as JSON contains usually big texts. This should be also effective. Okay, so there is some syntax that we propose for that. Create compression method. And then in create table statement, we just can use some compression method for any field. So compression methods are just have an implementing function which is written in C, and it is mentioned in the create compression method statement. Okay, and JSON BC is just a compression method which was invented by my colleagues for JSONB. It has a kind of dictionary compression and plus some variable encoding. This method of compression uses a special table for all the dictionaries. Probably next step will be separate dictionaries for different JSON fields, but now for simplicity it is the dictionary is common. Okay, some examples. Just we tried to find how effective is it. Okay, look here. So this is relational structure. This is JSON. This is JSON-B. This is JSON-BC. And this is B. So it means MongoDB, via Tiger engine. So what do we have? So the red ones means Postgres with Cfs compression. Cfs compression is a block level storage compression, which is also our patch. You see that it gives the best results, even better than via Tiger engine, which has some compression for JSON. Okay, but what with JSON-BC? This is a link to it. Probably I missed a slide, sorry, with JSON-BC. Ah, no, here is it. Oh, okay. JSON-BC is, you see, rather effective, but not. The surprise here is that Cfs compression is more effective than JSON-BC. Cfs is a block-level compression, which compresses blocks which are written to the disk. It is most effective in all cases. Okay, so you can experiment with JSON-BC. It is freely available. Okay, some benchmarks. The first benchmark was done late ago for Postgres 9.4. It was compared with some version of Mongo. We found that we also had some data set for testing, and we just used it to try our new contains operator and just query. So we found that Mongo is fast, but JSON-B is approximately same fast. But the index size is of the same order of magnitude, but if you the write performance is much better. You see, write performance is here. It's much better for Postgres. Mongo needed 13 minutes to insert all this JSON, but Postgres is much faster. Okay, this was old Mongo, old Postgres, and some artificial benchmark, maybe not very accurate. Then Enterprise DB published some benchmark on NoSQL, also comparing Postgres and Mongo. And they found that Postgres is rather fast, several times faster than MongoDB, both on inserts, on selects, and more effective in data size. We found that it is interesting, and also decided to make our benchmark. We tried to find some scientific-like benchmark, and we found that there is a Yahoo cloud servicing benchmark. It is just a benchmark for key value queries, so it is good to compare Postgres and Mongo. So there is some link to a paper about this test. We took rather big server for that. We took more than, at the time, MongoDB version, and defined some workloads with heavy updates, with read-only, and so on. Also, we tried to use a Cfs distribution. No, it means non-uniform distribution. Cfs distribution means that, for example, you use some small subset of the records very often, and it means that there is more locking on them. Okay, so these are the details of benchmarks. To compare Postgres with Mongo, we needed to turn synchronous commit off. And so this is what we tested. Functional B3 index. Why B3? Because this was a key value. So we just extracted records by ID, which was inside JSON. Also, it means that, so no, I don't remember actually what is it. J0, J1, don't remember. I will find it out and tell you later. Okay, so here you see client's number, and thousand of operations per second. The blue line is Postgres, and the green line is MongoDB. So we found that MongoDB is faster than Postgres only in some kinds of workloads. What does it mean? More than 500 simultaneous clients and Cfs distribution, so logs. For Cfs distribution, you see the difference between Mongo and Postgres is even bigger. So we found that there is a problem, and this problem probably doesn't, it's not a JSON problem, it's a Postgres problem itself. So this family is surprised by that, why updates are not good in Postgres, and this is the reason. So many backends are trying to update same rows, a small subset of rows, and something is ineffective with access to this small number of rows by big number of backends. So we found that there is some the log structure in memory which has n-square asymptotics. This has no good solution, no universal solution now for Postgres. So really, if you have many backends which simultaneously want to update some same records, then you will have n-square operation. But if you log primary key manually, then you improve performance. This is the workaround now. So when we tried to do this, we improved, you see, Cfs distribution, Postgres went better. So the optimized Postgres is the upper line here. It is better, and it doesn't go down. You see, this is the most F and A workloads are most illustrative here. The variant with locking unique keys makes Postgres much more effective. Okay, for Cfs distribution, the result is not so good, but also we have some improvement. Okay, so the conclusion from this benchmark is for uniform distribution, Postgres is definitely better than MongoDB if you use the optimization with logs. But for Cfs or other non-uniform distribution, Postgres may be worse in performance. So we need to make some work to improve the locking algorithms. Okay. These graphs just show that compression implements no overhead. Okay, next, I don't know why, but they want subscripting. They say that there is subscripting for arrays in Postgres, but unfortunately no subscripting for JSON. And it is non-convenient. Many people think so. And there is a patch for generic type subscripting. It is written by Dmitry Dolgov. It is on commit fest, probably it will be committed. So it allows you to write updates like that, to update some special key in JSON. It just simplifies using JSON, nothing principal, just syntax. Okay, so let's come to the conclusions. So Postgres is a good NoSQL database. You see that standard of SQL JSON is implemented in the best way, and we hope that Postgres 11 will have it. At least we will release it soon in next version of Postgres Pro database. Also, it's a new thing. It, of course, needs community support in testing, in documenting, in trying many functions which we don't probably understand much. Okay, there is some compression, which also is under work to commit it to Postgres 11, or at least to Postgres Pro 10. And Postgres is in most cases, okay, in some cases it is faster and more compact in data than MongoDB. So because of that, you can think that there is no need for MongoDB except automatic sharding. Postgres can replace it. Okay, so skip this. People behind Postgres. So Alexander Korotkov, Theodor Sigayev, Oleg Bartunov, who couldn't come here, Nikita, Peter Gagan, Andrew Dunstan, Robert Haas, Dmitry Dolgov. All these people contributed to JSONB. So now our friends are satisfied. NoSQL Postgres is good, but just we need to resolve the locking issue. After that, we could say, who needs MongoDB? Postgres is universal. Okay, so I come to the end. Postgres is really a universal database, and let us celebrate this. Thank you. Questions, please.
You had an interesting paper about the differences when to use JSON and when to use JSONB. When to use SQL JSON and not JSONB. This is missing.
Okay, JSONB is a data type. It can be used with SQL JSON. So SQL JSON is just a syntax. It is built on top of same data types. It just introduces a new data type for JSON path. Yes, please.
I think it was like a year or two ago that TotalDB was introduced. And MongoDB syntax on top of Postgres, which, as far as I know, in benchmarks quite consistently showed that it was faster than MongoDB. And were any of the techniques from TotalDB implemented in implementing JSON?
No, TotalDB is a quite separate solution. So it maps your structure into tables. It has some complicated structure of the tables, so it's quite different. But we believe that it's also fast. Yeah, please.
So I missed the part of this JSON BC. What was the goal of this BC?
So it's a compression. So it means that compression. Where is it? So the idea is to provide generic compression for any data types. Where is the slide? So we invented some generic syntax to define compression, create compression method. So here is it. Just we write some handler in C, and we can compress any data type, specify a compression in create table and in an alter table.
It's already committed?
No. It is on GitHub, but it's not committed yet.
So you can provide your own compression method?
Yes. So you can write your compression methods for any data type, for plain text, for example. Okay, thank you once more.